All right. So about time frequency decompositions. If you look at the signals shown here, what we would perhaps ideally like to get out in a plot of space or time versus frequency would be something that tells us that we have a certain frequency all the way switched on, because it looks like this is a pure sine or cosine that is running here through the background. And then at time point here 0.5, we have a bit of a blip added. And we've seen that the Fourier transform of an impulse is a constant. So to represent an impulse, we need all frequencies. So I have my impulse here. And this looks like a modulated Gaussian or something similar to it. So this, well, with a frequency that's very similar to what we've seen before. So it would perhaps be something that has a little bit of density there. So that is the ideal kind of plot we would like to get out. But so far we know only the spatial representation, where at each point in time I have the amplitude, and the amplitude at a single point in time, of course, doesn't tell me anything about the frequency. Or we have the Fourier representation, which looks only at frequency. And, well, if I plot the Fourier transform of this, I get a one-dimensional function, which will have a little bit of background everywhere, which originates from the pulse, and would then have a bit of a broad blip that comes from the Gaussian, and then the sharp superimposed by a sharp blip from the Dirac peak. So if I'm plotting only frequency, this is what it would look like. But any of these Fourier coefficients wouldn't tell me anything about where precisely the blip is and where this envelope is. It's only by taking all Fourier coefficients together that I learn something about localization. So at one extreme I have only frequency information, at the other extreme I have only time information, and wouldn't it be nice to have both? So I have another example of a signal here. Here is the cry of a bat, first shown in terms of a pure amplitude signal, and then in terms of a so-called spectrogram, which already gives us some kind of time frequency decomposition. So we have temporal resolution, we have frequency resolution, and we see a so-called chirp. So we have a signal here of changing frequency. And that is for a reason, by the way, because the bat wants to find obstacles and prey by echolocation. So it sends out a signal, and in some sense, if it could just send out a blip or an impulse, in a way this would be an optimum signal, because it's very compact in time. So it could measure precisely how long it took for the signal to travel to the object where it's reflected and back. However, for organisms, it would be hard to put a lot of energy into a blip. So, you can clap with your hands. That's one way of producing a blip. But if you have to make it with your voice alone, and this is what the bat does, it's very hard to put a lot of energy in a super short sound. And if you put too little energy into your signal, then it might drown in all the environmental noises that you otherwise have. So on the one hand, it wants to put a lot of energy into its signal, and on the other hand, it wants a good temporal localization of the echo. And if you're now asking what a signal will look like, which, when autocorrelated with itself, will have a very sharp response or autocorrelation, and then you find that a blip is, a chirp is the optimum signal. And this is what bats have known for a long time. So they use chirps. And here's a way of visualizing it. Yeah. No, yeah, that's what makes a chirp. So it's a chirp truly has a changing frequency. If it was a straight line, so something. Oh, I think the perfect signal truly has a curvature. I'm not perfectly sure. Okay, I would have to look it up. Okay, so summarizing again what I said about these two extreme representations, we have on the one hand what I want to call the Dirac representation, or we could call it a pixel representation, or if it's a temporal signal, we could call it an amplitude representation. So if I have time or space here, and if I have frequency or scale of the characteristic oscillation on the other axis, then for a signal of length 8, this is what it looks like. So we have perfect localization in space. So each bin here represents one value or one item of information, and our information pertains to time or space only. We have no frequency information whatsoever. And then we have a complementary representation, the Fourier representation, where we expand our signals in complex plane waves. And for a signal of length 8, this is what I get. So perfect localization in frequency, no information about spatial localization whatsoever. Now, if I want the best of both worlds, I can compute the short-term Fourier transform, or STFT. Again, sorry, my terrible writing. Short-term Fourier transform. And in most cases, and to obtain like a spectrogram that I've shown above, the signal is repeatedly weighted with some filter in space. However, this is not what I want to do here. So what I want to do here is look at a version where I use no weighting or no windowing, and also no overlap between those windows, because I want a purely non-redundant representation. And I can then obtain tilings such as this one here. I could say I'm splitting my signal in half along the temporal dimension. So what I'm left with is a length 4 signal on the left, and a length 4 signal on the right. And these signals know nothing about each other whatsoever. So this is why I can draw a thick black line here. Now for a signal of length 4, in a discrete Fourier transform, I only get out 4 frequencies. Or I could decide to split my signal into even shorter parts, so that I could say I'm splitting it in signals of length 2. And then for signal of length 2, well, I only find 2 Fourier coefficients, so I only get a low and a high frequency. So this is what my tiling would look like. So these would be length 2 signals. So on the one hand, I would like to have the good frequency resolution, as in on the left-hand side. Let's say this has a good frequency and this has a good temporal resolution. On the one hand, I would like to have the good frequency resolution, and on the other hand, I would like to have the good temporal resolution. So can I not just have both at the same time? Which, if I draw it in a picture, would look like this. Well, it's a rhetorical question, and unfortunately, no, fundamentally we cannot. So, no. Because of the uncertainty principle. So it's not a quantum mechanical phenomenon here. It's one of signal processing, but it's the same. It's actually the same proofs that are being used. So we cannot do this exactly, but we can have approximations to this. So, for example, it would be quite possible, if the signal is periodic, to say the following. I could compute a so here I have 8 frequencies, which means that I also must have a signal of length 8. And to get a signal of length 8, I could do the following. So in this column here, for example, I could weight my signal with a filter. I should draw it discretely, but I'm drawing it continuously here, which tapers off like this. And to get that column, I would use a filter which, thanks to the periodic boundary conditions, would look like that, and so on. So I could multiply these windows with my signal. I would still have signals of length 8, and these filters would imply that in this column here, for example, I'm mostly seeing the part of the signal located about here, but I'm also seeing a little bit of the signal from elsewhere. Now, if I make my filter narrower, then let's say like this. Now, if I make my filter very narrow, then I will keep a nominal resolution of 8 frequencies, but the practical resolution will be much lower because I'm only seeing, let's say, 2 or 3 discrete samples here, and from these I can only estimate something like 3 distinct frequencies. So in other words, yes, I can do it, but I'm really only interpolating in Fourier space. Y-axis has now in all these plots always been a frequency or scale, and the x-axis has been space or time. Yes, I always take, so for such, what I can do is, I can always, for each of these columns here, I can take my entire signal, but I'm weighting it beforehand. So I'm multiplying the signal with such a window, then estimating the frequencies. So this is the recipe for the more general form of short time or short-term Fourier transform, which has a couple of parameters, namely the window that I'm using, where the window itself has 2 things, namely it has a shape and a width. I'm calling these here as separate parameters because or you can amalgamate them into just saying the window, because let's say if I use a Gaussian shape, I could still have a small or a wide Gaussian. So I have the window, and then secondly, I have the overlap. In the extreme case, I could do this, I could repeat this procedure where I shift my window just a single pixel or a single time step. I can do it, but it will be, well, computationally a bit expensive if you do it for large signals. There is no information lost in computing a short-term Fourier transform, but there is also no information gained. So this is a redundant representation, whereas up here, these representations, they were non-redundant. So remember that the original signal had 8 values, and here I'm having 8 of these boxes. They're actually called Heisenberg boxes, thanks to this uncertainty relation. So I have 8 boxes in the left side. You know, in all of these images, I always have 8 boxes, 8, 8, and 8. Yeah, so here I need, or I have computed 64 values out of 8. But I cannot generate information by using such a transform. So it's, in a way, just a better looking picture that you get out. Okay, it can still be very useful, but fundamentally you hit this limit of the uncertainty relation, and you cannot circumvent it in this way. So this is a redundant or an overcomplete representation. And actually, this is still ongoing research. So there's the short-term Fourier transform. There are others like the Wigner-Will. Again, so many names from quantum mechanics. Wigner-Will transform, and there are others. Many of these transforms have so they're all transforms in the sense that you can compute the inverse transform. But the Wigner-Will, for example, it has this unpleasant property of generating cross terms. So if I have something that's located here in space-time and something that's located there, then the Wigner-Will transform will also hallucinate something in the middle. This hallucination, if you average over it spatially, it will go away. But if you do that, so actually if you smooth the Wigner-Will transform, you would get out the short-term Fourier transform. But anyway, so this is ongoing research, and there are people trying to look at images like the one that you've seen here, and to then come up with a simple parametric or semi-parametric description. So for example, you could say this entire image is a constant frequency, which is somewhere appearing here, plus this chirp term that I've drawn before, plus some noise term sitting down there. But these are heuristics. So this is there's as yet no deep mathematical formula that has been discovered that could do the job. Okay, so that's the bad news, but there is, don't be too disappointed. There's also some good news. I want to give you some useful references. So the book in the field is the one by Stéphane Malin, which I think is also available as a PDF. Then much less famous, but I also quite like this one, is by Alfred Mertens, which is a bit older. It's from 1999. It has the merit of being much shorter. So the Malin book, it's fantastic, but it's every edition is bigger than the previous one. It's going close on 1,000 pages, and the Alfred Mertens book is a quarter of that or so. And then just this morning I found the following, because I wanted to give the proper credit for some pictures that I'm using from Wetterli. Wetterli, so Malin was one of the leading figures in the development of this whole wavelet theory, and Wetterli also played an important role. He's in Lausanne, and he is right now writing these books, which are also available here as beta releases or alpha releases in PDF format. And I've leafed through, they also look very good. Okay, so I want to state without proof the two theorems that are the fundamental limit of all of the work in this area, and will then show what wavelets actually do. So there's a theorem that fundamentally you cannot get perfect localization in both space and frequency at the same time. The Heisenberg uncertainty theorem, which says that we have the temporal variance, which I should define. So the temporal variance is pretending that the function that we're looking at, or that its squared modulus is a probability density. Some normalization here. And U is the, let me write the center of mass. So the expected value of that distribution. So that's the temporal variance. And similarly, so the temporal variance simply measures the spread in space or in time. And we have frequency variance, So these are angular frequencies, so W would be 2 pi k. Okay, and these two are connected by the following inequality. Sigma t squared times sigma omega or W squared is greater than 1/4. This is what the theorem states. And equality is achieved for this function, which so often is special for a modulated Gaussian. Which in this field has a different name. It's called a Gabor function, after the same Gabor who invented holography, amongst other things. So modulated Gaussian is a Gabor function. So if I want to plot it, it would look something like this. So a spiral with a Gaussian envelope. So the amplitude here is just a Gaussian. Okay, here's one of the many figures that I've been borrowing for my last book for this lecture. Shown here are two modulated Gaussians, or more generally speaking, two wavelets, so one here and one there, along with their Heisenberg boxes. So these squares here are called Heisenberg boxes, and note that they do not delineate the exact extent, they just indicate the standard deviation along these dimensions. So it's important to, excuse me, so it's important to remember that these Heisenberg boxes here they are not the support of a function, or in our case here a wavelet. They just indicate its spread in space or in frequency. Now there are exceptional cases. For example, I can constrain my functions to a finite support in one dimension. So my function must be exactly 0 before and after some time. But they can then not at the same time have finite support in the reciprocal space. Speak up, please. Oh no, if it has finite support in space, then it's not a Gaussian wave packet, then it's, you know, a truncated Gaussian or whatever. So this is the subject of another theorem, which I think is sometimes called the Gabor limit. Which says that if we have a non-trivial signal, so it shouldn't be zero everywhere, if we have a non-trivial signal with compact support, then this Fourier transform cannot be zero on a finite interval. And vice versa. So in pictures, if this is the spatial domain, if I have some function that becomes exactly zero before and after a point and does whatever in between, it could be very smooth in between, then in K-space, as it cannot be zero on a finite interval, it must necessarily be non-zero everywhere for all frequencies. Given that such a short signal has finite energy, the values of the spectral density will be very low, but it will never be exactly zero. So I could impose in a plot like the above, I could impose a hard limit here, let's say in the temporal domain, but then it means that my signal is going to be have infinite support in the other domain, and vice versa. So I will leave you with some thoughts for the break. Namely, what kind of decomposition we would ideally like to have. So if you remember what the short-term Fourier transform gives us, if we admit no overlap between the windows, would be, for this, one of the possibilities I've been showing was this one here. However, if you look at an instrument like a triangle, it really matters when exactly, if you have a whole orchestra playing a piece, it really matters when precisely the triangle is being struck, which supposedly makes these triangle players one of the best paid orchestra members. I'm not sure if this is an urban legend, but you can really, it's amazing, as you can have a whole orchestra with 40 violins and so many oboes and horns, etc., and you hear the single triangle. It's amazing, and you want it to be struck at just the right time. So for a triangle, you would like to have a very high temporal resolution. You cannot have a good frequency resolution because it produces something that's, in the first approximation is like an impulse, so it will use many frequencies. And then on the other hand, we have instruments like this one here, where it's hard to make a very, very short sound. It needs to build up its vibrations and so on. So for this instrument, you don't care so much about temporal resolution, but you would like to know if the person hit the right tone. So you would want a good frequency resolution. And wavelets allow you to achieve a compromise, which of course still reflects the Heisenberg uncertainty relation, but it allows you to build patterns which look like this, where we have a good temporal resolution for the high frequencies and good frequency resolution for the low frequencies. And after the break, we will look at how to achieve this.